Good evening, everyone. Welcome to Advanced Course in Drones and Development. We have been talking so much about drones, which actually fly. And today is a time when we talk about something different, and that's about the rovers, which float underwater. But they are amazing because they still collect data and still do amazing things. So, to talk about that and his experience with everything else in conservation and wildlife, and his personal experiences with underwater ROVs, we have Shashank Srinivasan from Technology for Wildlife. Welcome, Shashank.
Hi, Ruchi. Thank you so much for that introduction. Yeah, it's great to see this session in play and to see all the participants as well. Yeah, I'd like to go straight into my presentation in that case. And just to give you a brief overview, I'm expecting to take about half an hour to 40 minutes on my presentation itself. And then I can spend as long as people have time for on questions and answer sessions or any other discussion you want to have as well about either the drones, the underwater robots specifically, otherwise any of our other work as well. So just go straight into my presentation. I'm going to start that up now. Okay, is this one visible to everybody?
We can see it in the PowerPoint mode. Do you want it like this or do
I,
you want it in the presenter mode?
I think you can. I should be able to see the presenter. Let me just try that again.
Sure.
Is that better?
Yes, perfect.
Great.
Thank
All
you.
right. Yeah. No, thanks. Perfect. Thanks, Ruchi. Yeah. So essentially, I'm going to talk to you today. It's about a very specific topic. It's about the submarine ROVs for conservation itself. I'm going to have a couple of videos to play for you as well, which are in the PowerPoint itself. So to go right into it and let you know a bit more about what we do at Technology for Wildlife. Essentially, we amplify conservation impact. That's our mission statement. And we do this through the use of appropriate modern technology. Now, in this context, it's very important for us that the word appropriate is used because we're very careful about how we use technology for conservation purposes. We try and ensure that no matter what happens, we don't cause any harm to either human communities or to the wildlife or to the environment in the areas we work in. There's more information about us up on our website at techforwildlife.com. And we're also quite active on Twitter and Instagram. The handle is Tech for Wildlife. So to learn more about our work, about what we do, please go and visit our social media or our website itself. We have contact forms there if you want to get in touch about if there are any questions about anything else. And I also have my email address at the end of the presentation if you want to get in touch with me directly. The two areas we focus on are geospatial data analysis and on robot operations. Um, Again, like today, I'm going to focus on specifically underwater robots. My colleague Nandini is going to be speaking in a few days about our other work, so I'll leave it to her to actually explain more about the other components of our work. That's a photograph of me with one of our aerial robots. So this is again, we've done some work in Ladakh, in Odisha, in like Goa, Karnataka as well. So we do quite a bit of work with our aerial robots. Again, like I mentioned, that's my colleague Nandini operating an aerial robot, a drone, and she'll be talking to you on Friday this week about our work with aerial robots. But again, to go back to today's presentation, specifically, I'm going to talk to you about submarine ROVs. And this is a photograph of one of our robots in Ladakh. We've named all our robots. So this particular one is named Paraha. And again, it's a SOFAR Ocean Trident. I'll tell you more about that in a bit. I'm going to play a video for you. This one's going to essentially explain exactly what the SOFAR Ocean Trident is, what it does. Yeah, again, I think it's a YouTube video, so there's also a link if you want to go watch it on your own later.
Does it have a sound, Shashank?
Yes, it does. Yeah,
We're not able to hear the sound.
Let me just see if I can continue. 1 second. Thanks, Ruchi. Yeah, is that better, Ruchi?
Can you put the video on so we can see if it's... Is the video moving?
Hi, sorry, Ruchi, is that clearer?
I can get an echo. Maybe when you share your presentation, no, you can share computer sound along with it.
Sure, I'll just do that.
No, we still don't see the sound.
Okay,
I
I'll tell
guess
you
we
what,
can go
I'm going
without
to,
it. No problem.
yeah,
You
sure.
can narrate.
I'll just play the video without it and then I'll narrate over it if that's any help, right? Yeah. So essentially, this video describes the Open ROV Trident. This video actually came out about 5 years ago, so it's actually quite a it's dated already, but we're actually using this device. They have been software updates, so it's actually easier to use now. They stopped manufacturing this robot as of actually May this year, but there are still some available, and again we have two of them in house, which I'll again bring up and talk more about. All right, I'm going to play the video without the sound, and I'm going to narrate over it as it goes ahead. So essentially, this is it came out of Berkeley in California. That's one of the founders on the right who's speaking to a reporter when they launched this device itself. It essentially is able to fly underwater, so it's quite maneuverable, very flexible in terms of being able to take tight turns, being able to go into narrow spaces. So it's been used to explore shipwrecks. It's been used to explored caves as well. So again, quite a nifty device. All right, it's got a camera in front, which is what's being shown on video now. It's got two thrusters on the back, which are horizontal, and one vertical thruster as well. So it's able to, go forward, backward, up, down, and also angle itself in the water, which is actually very useful in terms of looking at particular objects in the water itself. It's able to go up to 100 meters in depth, making it, much safer to use than a human diver, in that we can actually go into spaces which are too deep or too dangerous for a human to explore. That's a massive advantage of using underwater robots for this kind of work. That's a testing tank. So actually, I was able to visit them in 2017 and actually operate a Trident in this tank right around the time they launched it. And again, now for the past couple of years, people have been using it around the world. We've used it all over India in aquatic environments, in both in off the coast of the ocean as well as like in high altitude lakes up in Ladakh. Again, use it in a wide variety of areas. Right, I'm just going to, this is the kind of stuff you can do with it in terms of collecting lots of images and stitching them together to make 3D models. We've done some of that work with coral reefs, so you can actually, wear a headset, watch the robot as it's like operating underwater, and actually then even later with the data, look at all the 3D imagery collected. So that's that video. Again, I'd recommend like watching it with sound. It's quite interesting because again, since it's 5 years ago, the market for underwater robots has changed quite a bit since then. So the one I just showed you right now was the SOFAR Ocean Trident, which is, it's got 3 thrusters. It goes to 100 meters in depth. There's also the hello.
You're audible.
Yeah, great, perfect. Just checking. Yeah, thanks. There's also uh, the Fathom one, which is another commercially available drone. Three thrusters can go up to 45 meters in depth, and there's something called the Blue ROV, which has got six thrusters and can also go to 100 meters. Okay, now these are all commercial consumer level robots, which means that they're actually they're expensive, but they're not completely out of range of people who are doing projects in India. So, for example, we've got two so far Ocean Tridents right now. Both have come through grants. Each of them at the market costs approximately $2,000. The Fathom one is a lot cheaper. It cost $600 when it was launched. The Blue ROV is the most expensive of the lot. But again, I know people in India who also operate them for specific projects. Right. So again, it's they're like as expensive as like a small car in a sense, but they're still affordable. Some of the other robots I'll talk about like later in this presentation, they're not something you can actually look at buying for a project, right? They're customized, specialized. They cost millions of dollars, are able to go much deeper. But again, for most of the projects which we need to do from a conservation perspective, the drones on this page are more than sufficient. As a comparison, I've put in information about the other robots as well. It's important to know if you're working in the field of robotics for development, again, because it is possible to actually get work of this kind, where you can actually work as a robot operator, either in India or in other countries. And yeah, important thing to keep in mind when thinking of what skills you might need. So the next list of robots are, they're very interesting, but again, not really something which are easily accessible. So top of the list are the Sirius and Deep Discoverer robots. So these are actually a pair of robots, all right? The actual ROV is the Deep Discoverer. It's deployed from a ship based out of the US called the Okeanos Explorer. It can go up to 6,000 meters in depth and it's got manipulator arms, sample collectors, LEDs, and lots of other equipment as well. The other drone mentioned first, the Sirius drone, is actually a sled attached to the Deep Discoverer. So they operate as a pair of robots underwater. The main controllable ROV is the Deep Discoverer, while Sirius actually provides light and some other support functions to the Deep Discoverer. Now, the interesting thing about this is that this is also a tethered drone in that there is a wire connecting this robot up to the ship. This robot is expensive. It's in the tens of millions of dollars, and there's only like one of this particular type, right? So again, highly customized, very specialized for scientific research deep underwater. As you can see, it can go up to depths of up to 6,000 meters. That's 6 kilometers under the water. As a comparison, to go back to the previous slide, all these can go up to 100 meters. Okay, again, still deeper than most human divers can do comfortably, but nothing compared to the 6,000 meters the Deep Discoverer can go up to. What is common to both types of ROVs over here is that all three on this page are also tethered drones, which means that there's a wire connecting them to the surface, just like with the Deep Discoverer as well. Another form of robot which is very different from these tethered robots are something called ocean gliders. These are autonomous underwater vehicles. So technically, they're outside the scope of this presentation because they're not remotely operated the same way the others are, but they are autonomous, which means that they can be operated in either autonomous mode when they're out of contact or in remote control mode when they're within contact. All right. Now, the way these operate is that they can't go as deep as the Deep Discoverers, only up to 1,000 meters or so. But these are in constant motion and they can operate for months or on end, and they go across the ocean. So there have been, uses of these devices going from the coast of California off to Australia, right? So across the Pacific over a few months. Again, very interesting devices. I'm going to play a couple of videos for you, which talk more about these two particular robots on this page. Again, I don't think we need audio for them. I'm just going to play them, all right? The Deep Discoverer is the first one. And what's interesting about the Deep Discoverer's work is that there's actually a live stream underway, all right? So I'm going to play this again, no sound required. So this is a live stream currently from the Deep Discoverer. It's currently off the coast of the Atlantic coast in the US, from what I know, and it is being, they're doing a set of shakedown. So they're essentially sending it down to about 5,000 meters. Again, this is a live video, right? So this is happening right now. You can actually go and put it on and watch the live stream somewhere else as well. So this is the camera on board the device itself. When I played this earlier today, they were just like engineers and scientists around it setting it up, and we seem to have caught it right as it's actually entering the water. All right, so I'm going to let this play for about a minute, just so that you get a sense of what's possible with ROVs today. So I'm going to pause this and now move to the next video. Again, I don't think I could wait a full minute because it's showing water at this point of time. The next video is actually a capture from the Deep Discoverer earlier, I think in 2017, showing how it's actually found a really rare fish underwater at about, I think, 5,700 meters underwater. And actually, it captures like the behavior of this particular organism. So this video has sound, but you won't need it to actually understand what's happening. So this is the particular video, is the point at which they captured this particular fish on the camera itself. You can see the two red dots in the video, which is basically the lasers on the thing to measure distance. So what they believe, this particular animal is a sorceress eel found deep underwater. So essentially, they being able to operate the camera remotely, they've flooded the area with light, even though it's deep underwater, they can still see it clearly. Again, the two red dots, lasers from the device itself, help calibrate distance. So using that as a reference point, you can actually measure how long this particular animal is. You can look at how far away it is from the camera. You can do a bunch of other measurements, all right? This particular device, like I mentioned, the Deep Discoverer also has lots of equipment on board to collect data. So it's got sampling bottles, it's got these multiple cameras. But again, a big part of these expeditions for this particular vessel are that it's able to do this kind of live stream, all right, like, or to even capture this kind of data. It's amazing for ocean conservation, for scientific research as well. This kind of video is what actually helps convince people that it's important to avoid destructive activities in the ocean. So to look at seabed mining as a dangerous activity which could disrupt like rare wildlife such as this. Animals like this, it's possible, are even rarer than endangered wild animals found on land. And this kind of information about how they behave, what they respond to, where they live, is extremely important for conservation purposes. So it's so beautiful as well to capture wildlife like this, especially against the blackness of the ocean behind it. So that's the kind of video the Deep Discoverer 2, captures in the ocean itself. The other example I'd given you about ocean gliders, so this is a website which actually has more information about this. So this is oceangliders.org. You can see the website on the bottom left if you want to look at it yourselves. This essentially collates information from ocean gliders across the world. So you can go look at it. You can see what data is available. You can understand more about the gliders itself. Again, they're autonomous for the most part, but can be operated as ROVs. The main reason I'm including them is because they are important for conservation, and it is possible to again control them to. And again, they have a huge part to play as robots used in conservation and development activity. So this is how a ocean glider essentially works. So it uses ocean currents, the motion itself, to dive down, and then essentially it comes up again after that. Right? So it essentially moves like a sine wave under the water, and every time it surfaces, it communicates with like a satellite to get new instructions to transfer data as well. As you can see, they can go up to 1,000 meters of in depth as on the vertical axis, but that distance of 5 kilometers can take them up to 6 hours to traverse. Okay, so they move very slowly because again they use very little power because they're using the ocean's currents to actually move. So rather than propel themselves, they essentially have a rudder or a, in this case, an elevator, which allows them to change the depth in the water itself, which is the only moving part for the most, right? Because again, so that particular bit moves and it pushes the robot underwater. As it reaches its maximum depth, that part moves again and it comes up to the surface. So again, very interesting use of ocean currents and ocean physics to actually send robots across the seas. They move slowly, but they collect lots of information, and that's useful for climate change research as well as like marine biology. So again, that's what like the ROVs look like at a consumer at the scientific level, the specialized one. Going back to our vessels, again, what we do at Tech for Wildlife in India, we currently have two Tridents. Both of them came via grants for different projects. So one of them is from the National Geographic Society out of the US, and the other is from the Wildlife Conservation Society, also out of the US. Right. So these both got shipped to us. One in 2019 and one earlier this year, for work we're doing on coral reefs and in Ladakh on high altitude lakes as well. Again, this is what our projects in Ladakh look like. This is the ROV itself, the Trident, in a pool of water, not very deep. This pool is only about 1.5 meters, 2 meters deep, up in Himachal Pradesh at a place called Dhankar. And what we were doing with these robots was actually looking for signs of plastic pollution in the lake and to also capture video of animals living in the water. Because these bodies are at high altitudes, diving in them is very complicated, and therefore we like believe that robots are the best way to collect data in such difficult and dangerous environments. So this is again my colleague Nandini and me of putting the robot into the water. You can see she's holding a spool of wire in her hand. That's a tether itself. Um, it's attached to the Trident ROV with a waterproof connector, and then we can actually send it off up to 100 meters away from us or under the water while conducting our missions. The way we operate this robot is that again the robot is in the water connected with a tether to the surface, and we use a smartphone or another Android enabled device with Wi-Fi to actually connect to the robot when it's in the water. So the connection is essentially wirelessly from a phone to the tether, and then the tether connects to the robot underwater through the physical yellow connection. So actually operating it, that's my other colleague Gabriella, who's actually operating the drone. So she's got a smartphone in her hand, and they're actually controlling the drone, and she's watching the video live on her screen as the robot operates. So she can understand how to steer it, where to move it, based on what she's seeing on the screen itself. The what the way we use our Tridents is that we have that main small video camera which transmits high definition video live up to the tether and then to the phone. We also attach GoPros to it using specific mounts to collect stereo images and video, which we can then use for 3D modeling of coral reefs, of the bed of the water body itself. All this really helps in actually identifying areas of prioritization for conservation work going forward. Right? Again, data which would be impossible to collect without actually having a robot like this. This is another short video I'm going to show you. This is from Ladakh. It's from the bottom of a lake called Kyagar, which is up at about 4,800 meters above sea level. This is at about 5 meters underwater in that lake itself. And again, I've not started the video yet, but what you can see is all these small little objects in the foreground. Just going to play the video now, and you can see them all move around. So these small animals are called amphipods. They're like crustaceans, a bit like shrimp, and they're not uncommon. But from what I know, this is also the first video we have of these animals up at altitude. Again, because it's hard to actually explore these lakes and to see what lives inside them. From what I understand, this is the first video of these animals in this particular ecosystems. Again, stuff which is impossible to collect without these robots, and we are going to be collecting more data like this over the next couple of years. The main point of this mission to Ladakh was to look for plastic as well, and we did find plastic in these lakes using our underwater robots. I'm going to show you some video of that as well. Again, this video plays fast, and then it's also a version with slow motion at the end, so you can see the plastic bags very clearly. Yes, I have paused it at this frame. As you can see in front, that's the white shiny thing in the screen. If it's clear on your screens, is a plastic bag underwater. It's not very deep. As you can see from the top right of the image, it's only 0.2 meters underwater. But again, it's still plastic in the water, and this was pretty far offshore. It's about like 20 or 30 meters away from the shoreline itself. So again, as you can see, such plastic bags are quite hazardous for wildlife, such as the amphipods I showed you in the previous image. And this kind of data really helps actually prove how important it is to remove plastic from these lakes, to ban single-use plastic around these lakes as well. Again, and all stuff which we now know because of video like this, all right? That the fact that there is plastic in these lakes, it is dangerous to wildlife and it needs to be removed. Again, so we have lots of images like this of plastic, and this is one particular one I've chosen to share with you today. Just to talk a little about the Trident itself, as you can see on the screen, there are a few numbers up and around it. Starting from the top right, it's got the depth on the top right, that's 0.2 meters. It's got a temperature in centigrade under that, so that's 20.69 degrees in this water at that point of time. In the center figure of 170 degrees is a compass heading. So it lets us know which way the camera is pointing at any given time. So we know whether the Trident was going in a straight line, was it turning? It's got, it helps with like actually navigating it underwater, because unlike an aerial drone, GPS doesn't work very well underwater. So it's very hard to actually locate a device underwater. Our GoPros, which do record GPS, are able to capture some data near the shore, near the surface, but they quickly lose GPS signal once they go underwater. So again, navigating a Trident is much harder than flying a drone above water. And again, we can talk about that in the discussion session if that's of interest. To move on to the last bits of my presentation. So again, why do we use submarine ROVs in the first place? Well, when used appropriately, they can make conservation research and interventions safer, effective, and efficient. Okay, this applies to all robots in conservation, but specifically to submarine ROVs because of the fact that diving is dangerous. All right. Again, it's a skill. It's like a technical skill which can be learned, but every time a diver goes into the water, there is a risk associated with it. That means higher costs for insurance, for liabilities, higher risk in general, more equipment required in terms of medical kits. You need to be close to hospitals, all the things which involve sending humans into dangerous areas. The submarine ROVs, they're, if we lose a robot, we lose a robot. At worst, it's an expensive device, but that's nothing doesn't compare to the cost of a human life. So we highly recommend using submarine ROVs, especially in dangerous areas. Aside from what I mentioned here about safer, effective, and efficient, I also know lots of marine biologists who don't dive, right? They don't go into the water itself. So it's actually possible for them to use devices like this to collect data, to actually do very valuable research without having to risk their own lives or health going into the water. The other big reason is that they can collect large quantities of data, which can then be analyzed by computer vision algorithms, and you can obtain actionable information from them. There's only so much time you can spend looking at video on screen to actually understand what's happening. If you have automated ways of doing it, it makes life a lot easier. And again, because these ROVs can spend large amounts of time underwater, they can collect lots of data. when you have like computer vision, which can be used to actually analyze it, it makes things a lot more powerful. We are currently using a platform called TATOR, TATOR, which is based out of, again, the Nat Geo office in DC. And essentially what they're doing is using computer vision to analyze large quantities of video data, and all our data is being put through that system right now. So that kind of system automatically will be able to find plastic in the images, identify small wildlife in the images as well. Depending on how much information is available, it will be able to, try and guess what species of wildlife is found in the water. So again, very lots of information coming out which we can actually act upon and make decisions based upon. In India, we are collaborating with a group out of ICER Bhopal. So Dr. P.V. Sujit, who might be contributing to the lecture series as well, who's very much a part of the Flying Lab network. His lab, they have 2 blue ROVs. They do lots of computer vision work as well, and we collaborate with them quite closely on some of our projects. Just to get you a sense of, again, why it's important to use ROVs and what you can do with the data once you collect it. It's not really possible for a human diver to collect the same amount of data as a ROV can, all right? Like our Tridents can stay underwater for up to 2.5 to 3 hours, depending on the temperature. Human divers don't normally stay underwater more than 30 to 40 minutes. Again, so lots of comparisons we can do. I can talk about that more as we go forward as well. To close, again, that's my email address in the middle, and happy to talk to you over email about any questions you might have about my presentation. All right. I'm going to switch my presentation off now. If you have any questions, any discussion, we can do that right now. Thanks.
If you have questions, you can just make a hand raise and then we can have you. Yes, Ayan.
Hi, Shashank. Thanks for your wonderful presentation. So I just wanted to ask you about your work at Tech for Wildlife. So do you only have robot operations, or do you also engage in technology development?
Okay, so we don't participate in building technology as such at this point of time, because our mandate is conservation, which is what we're focused on. We try and use off-the-shelf technology as much as possible. So we have spoken to a few collaborators, in terms of, we've spoken to people who are building camera traps or smart fencing to give them inputs on how their technology can be more conservation friendly or can be more impactful, but we ourselves don't actually build technology in that.
Okay. And one last question. So when you are conducting these, when you are operating these robots, so do you do this independently, or do you collaborate with some private or government organization to assist them in their research?
Okay, so we do lots of assistance. We also have some of our own projects. So, for example, the Ladakh one was our own project, which was funded by National Geographic. But we've also done work in collaboration with the Forest Department, with marine research NGOs in Goa and in Karnataka to look at coral reef monitoring. So, in that case, we would use the ROVs to collect data and then give them the data they want. So, either we give them analysis in terms of what has been seen in the video, what data was collected, or depending on their capacity and capability, we'll give them the raw data itself.
Okay, thanks.
Yeah.
Thank you.
Yes, Siriak, sir. Siriak, sir. Siriak Joseph.
Yeah, sorry. Yeah, I was. Shashank, wonderful insight into. You're going a good insight into what happens underwater. So
Thank you.
It's a fantastic tool, I suppose. Nice presentation. Thanks for that. I got 3 questions.
Yeah, sure. Go ahead.
One is, what's your experience in muddy water?
Okay, so turbidity is turbidity is complicated. That's a great question. Do you want to ask me all 3 and I try and answer them all one after the other?
Okay, the second one is you talked about 3D
Okay.
modeling. So what do you do? Is it similar to the photogrammetry or is it something
Okay.
different? Okay. The third question is how do you get hold of positioning? You said GPS does not work underwater.
Yeah. Okay.
So and you
Perfect.
said you can go up to 100 meters or 1,000 meters or whatever. So you got a device which can be attached and get hold of the positioning, your
Okay.
X, Y, and
Got
Z.
it. Okay. I'll start with the first one in that case. So turbidity is a problem. Essentially, what that means for our underwater robots is in twofold. So one is the data collection itself goes for a toss, and the other is corrosion of the motors. Right. So we've had this problem. The Trident specifically had a couple of manufacturing issues when it was first produced. To talk about the Trident specifically, it's easy to replace the motors. Right. The reason again the underwater ROV market has kicked off is because it's cheaper to manufacture these robots when the thrusters. Again, I think I saw the question about what thrusters are, and as I so sweetly answered, it is the motor and propellers, right? So that whole unit is what we call thrusters, and essentially the all the ROVs I know of, like the Fathom one, the Blue ROV, the Trident as well, they use quadcopter motors, all right? So these are brushless motors which are exposed to the water itself because there's no contact between the essentially the stator and the rotor of that motor, the motor itself. So they don't conduct electricity and the water doesn't short circuit them because it's using magnetism to actually operate the rotation of that particular motor. So all the ROVs, they use exposed motors, which means that water enters the shell of the motor itself, okay, the bell, as it were. Now turbidity, what happens with turbidity is that like the small particles which enter the motor itself, they essentially scrape against the sides, exposing the raw metal to the water, and then there's corrosion. So for marine work with our Trident, every 2 dives we were throwing away motors. All right, so we did that a couple of times, and then actually found a easier way to do it. So we you lubricate them with oil if you can, but again we are very careful about how often we operate our Tridents in marine environments because there's a risk of losing
You can
the
pull it.
motor. Exactly. So again, it's easier for us to we can operate more frequently in fresh water than in marine water. So turbidity in marine water was a problem because it was turbid plus like salt corrosion as well. So that's definitely again that was about operational issues. In terms of actual data collection, turbidity means you can't again visibility is short, and these robots are primarily video operated. Okay. So again, that's a massive limitation for them. There are attachments. So for example, we are able to attach a hydrophone onto our Trident. We are able to use the Trident and sink it to the bottom and then essentially leave it in a park mode for a few hours. So it's not, the thrusters aren't kicking up any, mud of the seabed itself. Great for observation purposes once all the murk settles down. The moment you move it again, it throws the dust up again. You have to really keep that in mind. However, this is the same limitation as exists for human divers as well. It's exactly the same. So if a human diver can collect data, a Trident or another ROV can collect data. If a human diver can't because of turbidity, the same thing goes for the ROV itself. So on the balance of it, the pros outweigh the cons, and again, useful devices to have on board in a diving expedition. To ask your next question about 3D modeling, yeah, essentially it is photogrammetry. We collect lots of images. The GoPros are quite helpful because then you can collect dual images at the same time, which you can then stitch together. That's pretty much the model. So we use the same software packages we use for drone photogrammetry with our underwater ROV as well. The main difference is, which also answers your third question about positioning, is that because we don't have GPS lock at the bottom of the ocean, so none of our 3D models can be geo-referenced the same way our drone models can. If we collect enough images, then again, they stitch together accurately enough to create a 3D model, but positioning is very hard. Like we don't have a device which we can attach to it. They do exist, but they're, from our understanding of it, they're more expensive than the cost of the drone itself. But essentially, it consists of a acoustic receiver which can be mounted on the ROV, acoustic transceiver on the hull of the boat itself, which can pick up that signal, and then another one on the buoy to actually triangulate where it is. So that, again, for our particular applications, that kind of effort and positioning doesn't make sense. But again, because we are also we're doing research on, for example, coral reef mounts, so we can actually GPS lock the location of the mount from the surface itself, and then conduct our 3D modeling at the bottom. And again, you can then link the two of those together. But yeah, that's the positioning is again not a simple problem, not a cheap problem to solve anyway.
But what happens in depths of say 1,000 meters and
Sorry?
6,000 meters? What happens in depths when you're talking about 1,000 meters?
For those
I understand,
specialized.
sir. 150 meters fine, but then if you're going to 1,000
then
meters,
it's impossible, which is why the gliders, for example, the way they operate at the long thing, every time they come to the surface, they transmit their location. The same with the specialized ones, the ones I talked about, the Deep Discoverer, they don't have positioning on board, but again, those ships themselves, the NOAA, Okeanos Explorer and stuff, have very high-end sonar systems on board. So I don't think they have the same issues that we have with like the consumer level drones.
okay. Wonderful, Shashank. Good job also on your
Thank you.
other business side. Very glad to hear. No worry. Thanks. Thank you.
My pleasure. Thanks. Yeah, I'm going to answer this question from Krisha Shrestha, which I can see on the side. So essentially, it's a really good question. Like I mentioned, the Deep Discoverer, the specialized ones, some of them have manipulators on board, so they can actually, move things around underwater. The Trident, the one we have, again, even the Blue ROV, there are people who are modifying them. So you can actually have external arms attached to them, external, sampling bottles, for example, which open at a specific depth. So all these things they do exist. They can. In terms of how much it can collect, it depends on the power of it. Like I do know that, for example, with collection underwater, one thing which is worked especially for divers is that they pick up bits of plastic, put them in a basket underwater, and then use a flotation device to actually send it up. From my understanding at this point of time, it's still easier for that kind of really specialized manual work to have divers underwater. It's useful to have a ROV to actually find out where the large concentrations of plastic are and then send human divers down to those areas, right? So in this context, like at least with the current technology levels, it makes more sense to use ROVs to identify plastic agglomerations and then send people down there. So it saves you time and money in terms of having divers underwater, because you can just tell a diver to go straight to that point, collect all the plastic there, and then bring it out up at that point. So that's, I think, would answer the question about plastic underwater. Still doesn't make sense to use expensive robots for garbage collection, especially with the quantities involved in that case and the technical complexity of manipulating things underwater. I'm going to answer Shridupa's question next. This is very much in use in India. Like again, I know that there are, in terms of the Trident, we've got two of them. The groups operating in the Lakshadweep and Andaman Islands have about, I think, 5 of them in total as of March of this year. So there are about 6 or 7 of the Tridents in India that I know of at this point of time. I do know that when we got our device in 2019, that was the first Trident which came into India, because again, we had to deal with customs to actually import it. There are a few Blue ROVs in India, like I mentioned. I know there are at least 2 in Bhopal with Dr. Sujit at ICER Bhopal. They are around. Again, India is slightly more complicated, as Mr. Joseph had asked earlier about turbidity. Like most of our coasts have turbid water. So I know people who are working in Australia, in the Caribbean, in other places who use these extensively. For us, because of the turbidity, using them off the coast is slightly more complicated. But we are able to use them in freshwater lakes, which are clearer. So that's again very much used currently. Interesting observations. I know that at least one Trident in the Philippines, if I'm remembering correctly, got eaten by a great white shark. So there's a video of a great white actually going up and biting a Trident and then finding it's not edible and letting it go. So interesting insight into shark behavior. Worth looking up that video and actually watching a shark go chomp on the robot. That's definitely the most interesting observation I can recall with the Trident off the top of my head. To answer Ayan's question, to move forward quickly, in the Andaman Islands, I know that Dakshin and WCS out of Bangalore both have the Tridents. They got them recently. So the thing is that, again, because of the pandemic and the lockdown, I'm not sure if they've been able to use them there yet, but there are definitely plans to use them in the near future. One of the reasons the Andamans are interesting for robot use is because they have saltwater crocodiles there, which make diving dangerous. It's been banned for the past year, and again, so collecting data underwater is now very complicated because you can only use devices to do so. One of the projects I know that people have been conducting, which have been halted because of the ban on diving, is seagrass monitoring. So these are essentially large beds of seagrass which play host to wildlife such as dugongs, seahorses, all kinds of like endangered fish. To actually estimate how big they are, how far they extend, is something which you need to actually do observations of. So you have to do transects of them, which means going in a straight line, collecting data, video or images the whole way, and then analyzing it later. Because of the crocodiles, you can't do that anymore. So I know that there's definitely interest in using these robots to do that because, again, they're pretty sturdy. They survived a great white bite, and they'll probably survive a crocodile as well, as long as the tether cable isn't the one snapped. Yeah, I hope that answers that question. But yeah, there's definitely going to be more action with ROVs in India once the pandemic and the lockdowns come to some kind of termination.
Thanks, Shashank. There is also some questions about technology itself, like what are the thrusters and motors and propellers?
Sure. So the propellers in this context are the ones we have. They're all plastic, but you can also get them in aluminium or stainless steel to resist corrosion itself. They attach to the motor, and then essentially they propel the device in the water itself. So, like I mentioned, the blue ROV has 6 thrusters, which means it's able to operate across multiple axes. The Trident we have can spin left, spin right, tilt up, tilt down, go up and go down. Right. So it's got like about 3 thrusters. It's got about, I think, 4 axes of movement. So the more thrusters, the more maneuverable it is. The blue ROV is able to move in tight spaces. It can move fast because it's slightly larger as well, from what I understand. Again, these are essentially ways for a robot to operate underwater. Like I mentioned earlier, currently all the ROVs use quadcopter thrusters just because they're cheap because of the economy of scale involved in producing them. An important component of any ROV underwater itself. We've also actually been able to 3D print the propellers for a couple of our robots. So for the Tridents, for the earlier one we have called the Open ROV, which is much older. Again, I haven't spoken about it today, but that was a kit which had to be put together. So that one, when we lost some of the propellers because they got damaged while operating underwater, we were able to 3D print replacements for them. So lots of these devices you can manufacture parts using 3D printing or CNC technology to actually make them better, to improve the quality of material if you need to for specific environments.
Thank you, Shashank. Do we have more questions?
Shashank, you said Dr. Sujit is at Bhopal, is it?
That's right. Yeah, Dr. Sujit is at ICER Bhopal. He's very much a part of the Flying Lab network as well.
Okay. Is ICR, IC?
IISER. ICER Bhopal, yeah.
Okay. So he does something on the underwater drone research, or is he
robotics?
Robotics. Okay.
Yes.
Okay.
We have a question from Manira. Is it able to detect colorful objects? Do you have any plans to unleashing ocean minerals or collecting samples from the ocean?
Okay, so we don't have any sampling bottles on our devices. Again, our work specifically because we do lots of work around mapping and 3D modeling. We don't actually collect samples, but I know people who have done sample collection using these devices. They require, again, like you to add on parts to it, which can actually, collect things underwater. So either it's a sample bottle or it's a net with a manipulator arm. They do exist. Again, they have to be custom built by someone with expertise in that area, though. Colorful objects, interesting question, because like I mentioned, the whole computer vision component, that's very much a part of it, which is to be able to train a computer vision algorithm to actually identify objects of interest in video. So we are using, again, like I mentioned, something called Tator. So it's Pator. It's by a startup called cvision.ai, based out of the US. And essentially, Tator is short for annotator. And the idea is that since lots of underwater research collects, there's lots of video data collected over any mission, something like that is able to look through it and identify, for example, movement or objects of interest, something which stands out from the background. And then a researcher can look at only that segment of video as opposed to having to look through hours and hours of video on it. So that's colorful. That detection is, again, with the advent of the cloud, with all the with processing, with cloud-based programs. In that sense, we can do all of it remotely, where I have to just upload a lot of video into a cloud platform, and then they'll use GPUs based off the Amazon Web Services or Microsoft Azure to actually do any of the analysis required. But yeah, again, the thing is, once the data itself is collected, you can then use so many different platforms to look at colorful objects, to look at wildlife, to do any kind of research you want.
Thank you, Shashank. Do we have more questions? You can even unmute and ask if you all want. So Shashank, what are the main challenges that you have faced, especially when you're working in conservation, and it's not a very popular area where drones are used as of now. So what have been the challenges so far for you, and how have you overcome them?
Thanks, Ruchi. So one of the biggest ones was customs, because again, when we imported the Trident, that was a difficult one to do because there was a ban on drones in India. So it got stopped at customs in Delhi, and I had to spend about 2 weeks writing letters to customs officials saying that it doesn't fly, it has propellers, it's meant for underwater usage, it's meant for conservation research. And again, they were quite understanding, they let it through, but that kind of delay can take some time. Unlike aerial drones, permissions for this aren't complicated at all, because these are essentially tethered. So there's a lot, there's not much risk in terms of harming anyone else. Like at worst, the device gets lost underwater and then eventually floats to the surface. But it's not like an aerial drone can crash into people, right? And again, because they don't have any applications, commercial applications in terms of filmography, videography as aerial drones, there aren't that many of them. Like again, aerial drones, there might be a few lakhs of them in India today. Underwater drones, I'm going to assume there are going to be under 100 of them across the country. So again, permissions aren't a challenge at all for them. As I mentioned earlier, when Mr. Joseph had asked his questions, the turbidity is a problem. So environmental conditions are definitely something to keep in mind. Strong currents can throw your Trident all over the place, can I think I can see Amrita Lal on this call as well from Caerobotics. Again, she's an experienced operator. I've spoken with her about this as well, that operating ROVs underwater is much harder than operating a drone, because you don't know where it is. You can only see the perspective of the ROV. You can't actually see the ROV itself. So all you can see is the cable vanishing into the water, and we've had cases where the ROVs come up on the other side of the boat from us because, again, it's underwater and it's been pushed by currents. So navigating it is hard. It's definitely a skill that needs to be learned. It doesn't fly itself the way most modern drones fly themselves. That's been the biggest challenge for sure in terms of actually operating ROVs. But again, the benefits do outweigh the costs, because once you have the device, you have that capital investment in terms of actually owning a device. Maintenance hasn't been too hard aside from this motor replacement problem, and so much cheaper than a diver. We can go out on the fishing boat with some fishermen going out to catch water, collect lots of data, and then come back it's cheaper than taking an Uber the same distance. So that kind of thing is really useful in terms of collecting data.
So you've only worked in lakes, or you've also explored seas or rivers or other water bodies?
So we've explored in India. We've explored high altitude lakes. We've explored rivers as well in Goa and Karnataka, and we've also explored coastal coral reefs off the coast of Goa. So we've gone, a few kilometers of the coast up to maybe 20 or 30 meters in depth. Actually have a mission sometime this week where we're going to a few quarries which are abandoned mines in the Western Ghats, which are very deep waters. We're going to actually go and explore them and see what wildlife has taken up residence in those lakes. So that's actually happening on Friday. So I should have more interesting video from there. But again, quite a comprehensive set of aquatic ecosystems have been explored using our robots.
And do you perceive, like, would there be any risk if you're looking at flowing rivers, maybe not very fast flowing rivers, but at least flowing rivers? Would it be different there? Kind of the challenge might be different.
So what's good about the tethered robots is that all the modern designs, so all the Fathom, the Blue ROV, the Trident as well, the tether is can have a lot of strain on the tether, right? Which means that it acts to transfer data to and from the robot, but it's also essentially a safety line. So if the current is too strong, we can just pull the robot back to us. The problem again is when it gets tangled in the bottom, then it's much more complicated. It hasn't happened to us luckily, but I know people who had to cut the tether and leave the drone in a shipwreck, for example, in one of the Great Lakes of the US, because there was no way to retrieve it, too dangerous to dive, and couldn't be pulled back because it was stuck inside a sunken ship. So that kind of environment is complicated. But flowing rivers, again, we've collected some data in them, but at least in India, most flowing rivers in the lowlands are turbid. So that's been hard. We've used them in rivers up in the Himalayas, which have been beautiful. Again, not very deep, but be able to send it out to the middle of the channel, which you couldn't send a diver to in that environment. And then we've been able to pull the robot back to us after that.
Do you also see an application, for example, I don't know if you were doing that kind of project, but when you want to study the glacial lakes for any kind of, if you want to study flash floods, have they been used somewhere?
So that's we had a project which we were planning with the Nepal Flying Labs before the pandemic kicked in. But essentially, they've been working very extensively in Nepal on glacial lake outburst events. So looking at how when glacial lakes overflow and they burst, they essentially can, really submerge villages downstream, really cause devastation. So understanding how the bottom of a glacier looks, of a glacial lake looks, actually helps in understanding whether there's a risk to villages downstream, whether they need to evacuate them, and so on. So there have been experiments using boats, like autonomous boats which have sonar on them up in Nepal. We definitely want to use ROVs up at those lakes as well. Again, hasn't been done yet from my understanding with ROVs, but something we have planned for this year or next.
That would be interesting to know how that progresses.
Sure.
Thank you. Joseph, sir, do you have questions?
Is it for me? Yeah. Just want to know if you have any applications on rescue, because that's why I was more keen on muddy waters. So especially when floods are there, the waters are muddy. And then, and second thing, is there any other sensor other than just the cameras?
Okay. So this particular one, sure. The sensors on this device, there's a temperature sensor, there's a accelerometer to look at tilt, the compass as well to look at direction, and the main camera. So the nice thing again is that you can attach external sensors to it. Like I mentioned, the hydrophone. You can also attach again like cheap fish finders if those are available, in terms of being able to look at like basic single band, single reflection sonar underwater as well. So that kind of stuff does exist, but you can, again, it's modular, so you can add things onto it. Rescue, what I know of this, the only application is, because of the tether of the depth limitation, it's like, small ships which have sunk near shore with people maybe trapped in an air bubble. That's the only, again, I don't think these have been used for that, but the only application being discussed in terms of rescue has been around that. The limited tether range in terms of being 100 meters only means that if you're that close to your, your search and rescue object, then that's pretty much all you can do. Aerial robots seem to have much more application in terms of, being able to drop life buoys offshore to people who are swimmers who are drowning. Again, like submarine accidents, they need like military ROVs. So something like the Deep Discoverer, but again, specialized for military search and rescue applications. These commercial level ROVs, again, finicky to use in general. So it makes sense for research and conservation work, but I don't think you would be recommending using them during live setting events wouldn't be a good idea.
Okay, but I see a good application there, particularly during floods and flash
Yeah,
floods.
definitely like limited floods and flash floods. Again, like definitely like from my side, it would be mechanical in terms of being able to go out into the channel where a swimmer can grab onto it and be pulled back to shore. Again, the tethers can take up to I think 220 kgs. That's the rating. So you can actually really tug them to pull them back. So you can actually send them out that way. Yeah, that's definitely one way they can be used in a pinch if you had.
Yeah. Okay. Thank you.
Thanks. So I believe there are no more questions from anyone, Shashank. And we would also be collecting feedback from some everyone where again they can ask more questions if they have to. And many more people probably would be watching this video after this because some of them take like offline classes or they attend it like a separate program as well. So if that happens, we'll definitely, ask you if anything comes across, if anyone comes across a
Sure.
question or something. So for now, I would really like to thank you for being a part of this course, Shashank. It was great having you. It's always great learning with you. Thank you so much for being a part of this course.
Thank you, Chi. Really good to talk to all the participants as well. Like I mentioned, my colleague Nandini is going to be talking on Friday, if I got the schedule right, about our work with aerial drones for conservation as well. So she, again, there's a lot to learn from her as well on this topic because she's an experienced drone pilot in this area. But yeah, anyway, lovely talking to all of you, and I look forward to interacting with you again in the future.
Sure. Thank you.
Thank you. Yeah, bye-bye.
Bye.